in this lecture actually I will classify the low dimensional Lie algebras. So, let us try to classify the Lie algebras over complex numbers of dimension 1, 2 and 3. Okay. Let us see how far we can go. So, the one dimensional Lie algebra is somewhat easy to classify. Okay. So, we fix G to be a Lie algebra over complex numbers. If the dimension of G is 1, then it is easy to see that G is actually isomorphic to just this one dimensional space complex numbers with the trivial Lie product, okay, because G is abelian. Okay. The second thing, so let us look at dimension 2 Lie algebra. So, again there are two cases possible, one is abelian, another one is non-abelian. So, abelian Lie algebras we understand. So, we can assume that G is being non-abelian. Okay. For example, how the abelian will look like? Abelian will look like, so if it is abelian, so it is just spanned by two elements such that the products will look like bracket x y is 0, bracket x x, bracket x y y will be 0. Okay. So, like we said in one of the lectures, it is enough to actually give structure constant to give entire Lie product. Okay. That is what we are doing. So, I will leave it to you to check because there is nothing to check here because this is a trivial product. So, this will give you Lie algebra. So, now what will be the non-abelian case? Okay. So, the non-abelian case is actually is again not that hard, but let us see one example first and then we will actually get into the classification. So, here is one nice subalgebra of SL to C which is 2 dimensional. Okay. So, you take SL to C, so which is nothing but what, which is 3 by 3 matrices which are traceless. Okay. Then what is the dimension of SL to C? So, sorry, this is 2 by 2 matrices. So, this is the dimension is 2 square minus 1, so which is 3, and there is a natural basis which we fix. Okay. So, fix the basis. What is the basis? We call it X, which is the upper triangular matrix, and then H is 1 0 0 minus 1 and Y as this lower triangular matrix. So, these are all inside SL to C and that will form a basis. Okay. So, now what we do, we take this C span of this lower triangular matrix 0 0 1 0 and off times this H 1 0 0 minus 1. So, this is sitting inside SL to C. So, this is a naturally a vector space. Now, it is not hard to verify the bracket that we have, commutative bracket on SL to C will give you Lie algebra structure on this. So, that means this is a Lie subalgebra of SL to C. So, how to verify this? Let us verify this 0 0 1 0 using the elementary matrices. This is just E21 and this is nothing but off times E11 minus E22. So, if you compute the Lie bracket E21 comma off E11 minus E22, you can see that this immediately gives E21. Okay. So, this is a simple check. So, that means these are all the Lie brackets on this subalgebra. So, E21 commutes, and this of E11 minus E22 that also commutes, and when you take bracket between them you get E21 back. Okay. So, these are all the brackets. So, indeed we prove now that any two dimensional algebra will be isomorphic to this algebra. Okay. That is the result. Okay. So, for that let us start with G, which is two dimensional Lie algebra. So, we assume that G is not abelian. Okay. So, what is our claim? Our claim, this G is isomorphic to, maybe call this as G2 non-abelian. Okay. Non-abelian. So, that is what I am calling it. So, G will be isomorphic to G2 non-abelian. So, for that we need to establish the basis of this G that will have similar this Lie product that is there for G2 non-abelian. Okay, let us try to do that. First of all, recall what is this derived algebra. So, this derived algebra is nothing but span of all these commutators, okay, where x y comes from G. So, it is easy to see this derived algebra. Okay. So, this is the derived algebra over the derived algebra of G. So, then this derived algebra is an ideal inside G, and we also have this center. Okay. So, this is the center, this is those G in G such that the bracket x G is 0. So, this is the center, this is also an ideal inside G. Okay. We have these two important ideals inside G. Now, let us try to use them and then see what happens. Okay. Now, this G is not abelian, that means the derived algebra must be non-zero. Okay. So, G is not abelian, that implies the derived algebra is non-zero, and actually it is not hard to give the following characterization. Okay. G is abelian, so the following are equivalent. G is abelian and the derived algebra is 0 and the center is full, and the fourth thing is add x map is 0 for all x in G. Okay. Similarly, you can also say add map is identically 0. Okay. So, these are all the characterization of abelian. So, now we started with G which is not abelian. So, the derived algebra should be non-zero. Okay. Now, what will happen to the derived algebra? Let us say suppose Cx and Cy that spans G, then what will happen to Gg? So, the Gg will be spanned by this xy, because bracket xx is 0, bracket yy is 0. So, only the bracket xy will survive and that is going to span Gg. So, now this is actually a non-zero space. So, you can get x and y, that is the basis of G, such that this bracket xy is non-zero. Okay. We already proved one exercise. Whenever you have two elements in G such that bracket xy is non-zero, then both elements must be linearly independent. You can also use that. So, that means you have a basis. So, we have a basis xy in G such that this happens. Okay. So, now what you can do, you can take some non-zero element. Okay, you can take this x y itself, but all I need is some z in GG, which is a non-zero element. Okay, so then I can extend this z to a basis of G. Okay, extend this to a basis of G. So, then what happens if I take the product z tilde, so that has to be some multiple of z. Okay. So, note that this has to be non-zero. Okay. This for some alpha non-zero complex numbers. Why? If this is 0, then that will say that the bracket GG is 0. Okay. So, now what you can do, you can replace z tilde by this alpha inverse of z tilde. So, you can take for example, x equal to z and y equal to alpha inverse of g tilde. Then you can see that the bracket x y becomes equal to x. Okay. So, it is not hard to see, again G is spanned by this x y. Okay. That implies we have a basis x y such that the bracket x y is x. Okay. But if you go back and then see our G2 non-abelian, so if you take this E2 1 to be x and then this half times E1 1 minus E2 2 by y. So, then this bracket x y is nothing but x. Okay. So, the bracket x y is x. So, that means the Lie algebra that we have actually dealing with contains a basis x y such that the bracket x y is x. So, that means this G must be isomorphic to G2 non-abelian. Okay. So, what we proved? We proved that in if G has dimension 2, then there are only two possibilities. One possibility is G is abelian. So, that means this is G direct sum C abelian. Otherwise, G is isomorphic to G2 non-abelian. There are two Lie algebras of dimension 2 up to isomorphisms. So, now let us get to dimension 3. Okay. So, dimension 3 is actually bit more complicated than dimension 2 and there are actually various Lie algebras that we will see. Okay. But what I would like to do, I would like to recall some of the important Lie algebras, okay, which will be very useful later when we develop this structure theory of semi-simple Lie algebras. Okay. So, here are these Lie algebras. So, we already seen one example. So, what is that example? That is SL2C. So, at SL2C as we actually denoted this is 3-dimensional Lie algebra which has this basis. So, whenever we actually talk about SL2C, we fix this standard notation C x, C h and C y, where x denotes this 0 1 0 0 and h denotes the diagonal matrix 1 minus 1 and y denotes this lower triangular matrix 0 1 0 0. Okay. Then it is not hard to compute the structure constants. So, if you do the computation, you can see that the bracket x h x is nothing but 2 x, the bracket h y is nothing but minus 2 y and the bracket h h is 0. Okay. Similarly, the bracket x x is 0 and then the bracket x y will be h and the bracket h x is already given, okay, and then the bracket y y is 0. Okay. So, if you carefully look at it, this thing actually makes add h is diagonalizable, because add h has eigenvalues 2, 0 and minus 2 with the eigenvectors x, h and y. Okay. These are all the eigenvalues, and these are all eigenvectors, and that makes add h diagonalizable. Okay. That is a very important observation. So, now let us see some structure about this SL2C. What I mean by that, as Lie algebra, what this Lie algebra, that one can ask. So, we can prove that this is indeed simple Lie algebra. So, this is the very first example of simple algebra, Lie algebra that we are seeing. So, claim SL2C is a simple Lie algebra over complex numbers. Okay. How do we prove? So, we need to prove that first of all dimension is more than 1, we do not need to worry. So, we need to prove that if you start with any ideal, that must be either 0 or full. So, let us start with non-zero ideal I inside SL2C. So, now what we can do, we can take this add h map and then restrict to I. So, then you will get a map from I to I. Note that add h is diagonalizable. So, that will imply add h restricted to any invariant subspace will be diagonalizable. So, that means add h restricted to I also will be diagonalizable. In particularly, I can write I as direct sum of eigenspaces for this add h, but 2, 0 and minus 2, these are all the eigenvalues, okay, of this add h. So, that will tell you that I can be written as only the eigenvalues corresponding to these. So, I 2, I 0 plus I minus 2. So, what I mean by I lambda is the eigenspace of I that corresponds to the eigenvalue lambda of add h. Okay. So, now you have this eigenspace decomposition. Now, you can see that suppose this I 2 is non-zero, let us say. So, once you go back and then see what are all the eigenvectors of this add h, those are all nothing but x, h and y. That means, each eigenspace, okay, that corresponds to eigenvalues of add h, they are all one dimensional. Okay. That means, if you take any of this eigenspace, okay, so I lambda either it is 0 or the dimension of I lambda must be at most 1. Okay. So, that will tell either I lambda 0 or I lambda will be equal to SL2C lambda. Okay. So, that is the observation. If you use that observation, if I 2 non-zero, that will imply that I 2 must be span of x, okay, because x is the eigenvalue vector corresponding to 2. So, that says this x must be inside I 2, but once x is in I 2, then you can see that x bracket y which is h, that is also in I 2, but then that will imply h bracket y which is minus 2 y, that is also in I 2. So, that implies x, h, y all are in I, okay, x is in I 2 implies bracket x y is in I, and similarly bracket h y is in I. Okay. So, that will imply x, h, I, y all are in I. So, that imply I is SL2C. So, similarly, if I 0 is non-zero, that would imply H is in I. So, that would imply immediately H x which is 2 x and H y which is minus 2 y both are in I. So, that will imply both x and y they are in I. So, that will imply I is SL2C. So, similarly one can prove for I 2 non-zero I minus 2 non-zero would also imply I equal to SL2C. So, that means we proved that I is SL2C in all cases. So, that proves that SL2C must be a simple Lie algebra. Okay. So, now we will actually give another important Lie algebra called Heisenberg Lie algebra, which is also can be identified as a subalgebra of some general linear Lie algebra. Okay. So, what is Heisenberg, which is again very important 3-dimensional Lie algebra. Okay. So, we will see later what type of Lie algebra this is, but right now just focus on the definition. So, you take these 3 by 3 matrices which are spanned by E12, E23 and then E13. So, this is inside M3C. So, you take H to be this. So, then it is easy to see the following is the Lie product and this is actually a Lie subalgebra of GL3C. So, what is E12, E23? So, that is E13 and then the bracket E13, E12. So, that is 0. Similarly, bracket E13, E23 that is also 0. So, if you call this E12 x, E23 y and E13 is z, then basically these Lie products can be read as follows. So, this is just x y being z and z is in the center. Okay. So, this way you have given all the product, because this is a Lie subalgebra, there is nothing to check because the Jacobi identity and all will be true. But you can also start with x y z spanned by x y z which has this Lie product and then directly check, that also will form a Lie algebra. Okay. So, now let us classify or the characterize this Heisenberg Lie algebra. Okay. So, yeah, before that let us see like what are all the types one can get in the dimension 3. Okay. So, I will actually do some of the cases, I will not be able to do all the cases. So, I will leave one case as exercise, remaining cases I will do. Okay. So, here are the cases for dimension 3. If you take G to be a Lie algebra which has dimension 3 and assume G is also non-abelian, because abelian Lie algebra we understand well. So, then the following things are possible. So, like I said, you have the derived algebra as well as you have the center. So, in terms of the derived algebra and the center, you can make following assumption. So, the derived algebra has to be non-zero and the center has to be proper. Okay. So, because G being non-abelian. So, now that means the dimension of the derived algebra, it can be either 1 or 2. Similarly, the dimension of the center, so it also can be either 0, 1 or 2. Okay. So, now we classify them according to this. The case 1 will be the dimension of the derived algebra being 1 and the derived algebra being a subalgebra of this center. the case 2 will be the dimension of the derived algebra is 1, but it is not contained in center. Okay. The case 3, which is actually most interesting case, and in this case we will have lots of possibilities. So, where you just assume the derived algebra is has dimension 2, and the case 3 case 4, where you assume that the dimension of the derived algebra is 3. Okay. So, I will tell you like what are all the things that we are going to get. In the case 1, we get this Heisenberg. Okay. So, in some sense these assumptions will characterize Heisenberg-Lie algebra. In case 2, we get what is called this direct sum of 2-dimensional non-abelian and 1-dimensional abelian. So, it is basically G2 non-abelian, direct sum G1 abelian, where G1 abelian is nothing but C, okay, 1-dimensional abelian. In case 3, there are infinitely many possibilities, okay, infinitely many possibilities. Later we will see like what type of Lie algebras they are, but even in this special case where the dimension of the Lie algebra is very small. So, we are getting actually lots of possibilities. In case 4, what we get is actually isomorphic to SL to C. Okay. So, we will introduce later what is called this solvable Lie algebras. So, basically this case 1, 2, 3, all of them will be solvable. Okay. And in case 4, you get what is called simple Lie algebra. So, which will be a first non-trivial example of semi-simple Lie algebra. Okay. So, this is how the picture of dimension 3 looks like. So, what we do like I will actually only do case 1, case 2 and case 4. I will leave it to you to think about case 3, which is very interesting, and more or less the ideas that will be used in classifying this case 3 will be already presented in all other cases. So, it is actually a very good exercise for you to think about this case 3. Okay. Now, let us focus on case 2, because case 1 is already done. Okay. Yeah, we still have not done case 2, case 1. So, let us focus on case 1. I guess just gave the definition of Heisenberg. Yeah. So, what is case 1? You take the dimension to be 3 and the derived algebra is inside the center. Okay. And the dimension of the derived algebra is 1. So, these are all the conditions. Note that all these conditions are satisfied for the Heisenberg. Okay. So, now what we do, we just start with the basis and then see what we can tell about the structure of the Lie algebra. So, take f g z be a basis of this G. Okay. So, then this f g, the bracket, so that has to be equal to Z, and I can assume Z is also coming from the center. So, why I can do that? So, again from the previous argument, this is actually easy to see because the dimension of this derived algebra is 1. Okay. Suppose if you take a basis x y w, so this is the basis of G, then you can see that this the derived algebra, okay. So that will be actually okay. So maybe like we can actually do it another way. You start with some basis of this derived algebra because this is one dimensional. So you can pick some f g inside G such that the bracket f g is non-zero. So once this is non-zero, then the bracket g g will become span of this f g. Okay. So now what we claim, if you call this z to be this bracket f g, so then one can claim that this f, g and z that will be linearly independent. Elements of G. Okay. So, once we verify this claim, then we get this basis, okay, because the derived algebra is contained in the center. Now, why we actually get this as linearly independent? Let us see. So, you just take alpha f plus beta g plus gamma z to be 0 for some alpha, beta, gamma coming from C. So, we need to prove that all these alpha, beta, gamma are 0. Now, what we can do? We can then simply apply, okay, add G here. If you apply add G, then what do you get? Apply add G. So, then we get this will be alpha G f plus beta G g will be 0 and then beta Z will be also 0 because the derived algebra is contained in the center. Okay. So, this plus 0 equal to 0. So, that will imply alpha minus Z is 0. Since bracket f z is nothing but f g is nothing but z, so g f is nothing but minus z. So, that will tell you alpha must be 0 because z is non-zero element. Okay. So, now you have beta g plus gamma z is 0. So, now apply add of f. If you apply add of f, you get beta f g plus again gamma f z which is 0. So, then you get beta f g equal to 0, again bracket f g is z which is non-zero. So, that implies beta is 0. Okay. So, f z is 0 because z is coming from the center. So, you get alpha beta 0 and since z is non-zero, so gamma also 0. That proves that this f g z they are all linearly independent elements. So, now if you just put them back, so what you are getting, G is nothing but span of f, g and z and the bracket f g is z and z is in the center. So, that simply says G is isomorphic to the Heisenberg algebra. Okay. So, this is the proof. So, maybe I will actually continue this classification in the next lecture because we are running out of the time. So, we will stop here. Thanks.